Right. So we are take back the equation that will be used in the um, quiz 1B, where this is the local velocity distribution in a steady one-dimensional laminar flow inside a pipe. We how we can solve this problem. Before that, I would like to show you the differences between the average velocity profile and the local velocity profile, which is the actual velocity distribution that could be expected from laminar flow of fluid inside a smooth pipe. So the one inside the square red square box there represent the velocity profile, average velocity profile that we will always use in majority of the topics in the courses. And the actual velocity distribution is given by the parabolic distribution of velocity profile um, that you can see. You can have zero velocity at the wall and its maximum at the center line of the tubes of the pipe. So this represents one-dimensional, incompressible, steady laminar flow. Right? And then change the distribution in the figures from u function of radial to v function of radials. Similarly, the average velocity is using the same symbol. Right, as I said, uh, the actual velocity distribution is very important when we go to learn the topic related to losses, major losses in the pipe, right? So when we are said major losses in the pipe, I mean it's not pipe fittings like the entrance or at the band, right? So major losses will refer uh, uh, to the pipe itself. Now, in the quiz 1B, the question that you need to answer is to calculate the mass flow rate. Um, and if you want to evaluate the mass flow rate based on the small uh, cross-sectional areas that flow through the pipe, we need to integrate the if just these small time rate of mass flow through that cross section with the limit from r equal to 0 actually at the center line of the pipe up to the radius of the pipe, which is r. R is equal to a diameter divided by 2. So if you look at the equation after we replace the distribution of local velocity, we find that the mass flow rate can be determined if we know about the pressure differences and then the fluid property, which is dynamic viscosity, the geometrical properties of the tubes, which is the diameter or the radius of the pipe. Now, I'm going to show you the method how we can evaluate the function inside the integrations using the uh, online integration calculators or integration solver. Right. So what we can see here, I have two section here. The one on the left tell us about the fluid, right? This one actually is a fluid, and we would like to evaluate the cross-sectional area, mean at plane, right? At one plane along the pipe axis. So we are looking at a section here, the gray color, and the thickness of that thin layer cross section here is dr, and the location of this circular strip is r from the center line of the pipe, right? We are looking from the side view. This is a side view of the pipe, and the radius is given by capital R here, and we would like uh, to get the all cross sectional area for this fluid, right? We are not talking about cross sectional of the pipe outside, no, but we are looking for the fluid. So we have to know what is our region of interest. Region of interest here is a fluid. Before I go further, this is a website from Symbol Lab, right? So they have an integral calculator that you can find online. Right, finish with that. So in this integral solver, I'm going to take the integral symbol here from the menu here, right? So just take the one with the um, limits. So we have r equal to 0, and at the maximum is d divided by 2. The reason why I don't use r here, because the solver will simplify the symbol and it become small r, so we cannot get the actual integration solutions. And then in the I just use only part of the equation. I just take 1 minus r divided by d divided by 2, right? So we have power of 2 there, so we just select this symbol, so it gives you the power of 2. Similarly for the bottom, I just select power of 2, so we have r2 divided by r, actually r, the diameter of the pipe, the radius of the pipe, and then we have dr, right? So I left the 2 pi from the outside from our equation. What we need to do is to click go. So the system will do the solver will do the calculations, so we can find the steps in the calculation if you not remember. So you minimize the effort here to understand the problems, and leave if you forgot the step how to do integration, so the solver will help you to recall back what you have not what you have forgotten. So here we can after we set the limits, so we can get the solution of the problem based on the diameter of the pipe. Right, so we come back to our main slides here. So just to remind you again that another assumption that we're going to make for this problem is a constant property fluid, because one of the fluid property here, dynamic viscosity, is constant. So the dynamic viscosity here is given by mu, a Greek letters, right? So I just mark it here with the circle, red circles, and the numerator here will be the pressure difference. These are generic names, but in our case, the problem that we look at, we're going to call pressure difference here as a pressure drop, because you can see that in the manometer, the water column or at the downstream direction is much more higher. It means that the pressure is, there is much more lower. So I just show you the location of the orifice. As you can see that we are, for this schematic diagram, we are measuring a flow of gas in the gas phase, because the manometer fluid is much more dense than the gas. So we have to place it at the bottom of the pipe. So if the problem involve uh, an increase of pressure at the downstream location in the flow, so we're going to call it pressure rise. So again, I want to recall again, pressure difference can be pressure drop or pressure rise. But like one of your friend asked, Muhammad Afiq asked, the diameter is not the final answer that you want to calculate. The final answer will be the mass flow rate and volume flow rate, as well as the average velocity of the fluid that flow inside the pipe. So just to remind you again that the diameter, actually the one I'm drawing now, so that will be the diameter D, right? The D is the diameter of the pipe. So we don't, it is given, I think, 50 millimeter. So we have to convert it into meter. It become 50 divided by 1000, which is equal to 0.05 meter.